Hello, morning. We had the midterm 3 on Friday. I haven't graded it yet, hopefully before the next class. But how was it? Any general comments? What's reasonable? One of you says it's not reasonable. I'll go through it and we'll get back. The homework 10 I have uploaded, it is due next Monday. We'll have another homework due 11 on the following Monday, and the 12th homework will be due on the last day of classes, and this will be optional. Optional in the sense that if your homework grades on an average is lower, then this is a time for you to compensate for the homework. But if you have full score, you can afford to skip the homework. But having said that, the contents of the homework are important. It is relevant for the final exam, so you cannot just ignore the content of the homework. So that's how it will go. And final exam is on May 2nd, Monday. We introduced the idea of electromagnetic waves. Let me change the camera before I forget. We introduced the idea of electromagnetic waves. We said that if electric field is oscillating, that means it's changing, then it can induce a magnetic field. And if the magnetic field is changing, it can induce an electric field. And these two changes, if done in a certain way, can sustain each other. So that is, electric field can keep creating the magnetic field, and magnetic field can keep creating the electric field. This in many ways is the idea of a light wave that we introduced. And here we want to talk about how light waves propagate, or how do they interact with each other at interfaces. So this is broadly called ray optics. Why a ray? We will bring that up in a few minutes. Optics means the study of light, especially when light interacts with materials. If there is an interface, when you see yourself in a mirror, light is actually reflecting off the mirror. And why Why do you see your left, when you lift your right hand, why does your left hand in the mirror lift up? Those kind of ideas we want to address. To begin with, light itself, or electromagnetic wave. Electromagnetic wave. We saw that the change in electric and magnetic field is a wave, in the sense that the actual changes are happening in a certain direction, but the propagation of energy is happening in the perpendicular direction. So this is the direction of propagation. But even though energy and momentum is being transferred in that direction, the actual electric field is oscillating perpendicular to that. So that's electric field. And let me say this is electric field. So it keeps oscillating. Notice that it is oscillating perpendicular to the direction of propagation. In fact, whatever is oscillating, it doesn't change or move in the right direction, in the propagation direction at all. But as a whole, energy and momentum is being transferred, very much like an ocean wave. In this case, in an ocean wave, there is only the magnitude by which the water is going up and down is the only quantity that is of importance. Here, there is another quantity, that's a magnetic field. So that's in the third direction. One of the direction is direction of propagation. Electric field and magnetic field is perpendicular to both of them. And that's also oscillating, and they are in phase. So when electric field is a maximum, magnetic field is also a maximum. And that's your electromagnetic wave. What we would like to now do is, what happens to this wave when it approaches a interface? In particular, let's say it's a glass surface. So what happens to this electromagnetic wave when it reaches a surface? So this is a rough surface, let's say glass. And even though whenever we look into the mirror, it seems like it is the glass that is the relevant property that is of importance here. We will notice that it is a conductor that is important. So we have seen that electric and magnetic field interact with charges. Right? Glass itself doesn't have any charges on it, so we need to have charges. So charges are freely available on a conductor or inside a conductor. So somehow we want to bring in a conductor, and if you notice on your mirror, so there is a thin layer of metal that is pasted. In fact, you spray this quantity on the at the back side of the mirror. So the main idea is that it is actually the metal that is acting as a surface or as a mirror, but metal is usually expensive, whether it is silver or gold or copper. Most of the metals are expensive, especially if you want a thick piece of metal. So what you do is that you take a glass material, which is significantly cheaper, and you can get a smooth surface on that, and you spray a very thin, as thin as possible, layer of metal. So this is a thin layer of metal. Which means to say that whenever we are having a mirror in front of us. It is not the glass that is important, it is a metal. So what happens to a metallic surface? So let's now ask, there is a metallic surface here. So this is metal. And it doesn't have to be so flat. It is usually not easy to get a perfectly flat surface. And let's talk about what happens when there is an electromagnetic wave coming and coming towards a metal. These are electric fields that are oscillating. So electric field oscillates if there is an electric field that is very close to a metal. Metal has charges, so the charges inside the metal oscillate. Like that's what basically it does. Electromagnetic wave has electric field, oscillating electric field, that makes the charges in the metal oscillate. And these charges in turn make sure that this reflect back. So it creates a new field. So this creates a new field and it can reflect back. And what is the frequency and wavelength of that? So that's what is important. But before that, we have to ask, it is important that this is really flat. If this is a flat surface. In practice, most of these surfaces are not flat. When we think of a cloth, that's not a very flat surface. So electromagnetic waves interact differently with a metal and a non-metal. Metal especially is possible to make it flat. So we will talk about situations when the surfaces are really flat. And then you say that, what do you mean by flat when eventually everything is made up of atoms? Perfectly flat materials are not available. So how can we, what is the definition of flatness here? So if the wavelength of the wave we are talking about, electromagnetic wave has a wavelength all the way from 0 to infinity. If the wavelength is larger, then the roughness of interface, then it is called a flat surface. And that immediately tells us that flatness depends on what wave we are talking about. If we're talking about a gamma ray, then flat surfaces are almost impossible because atoms are bigger than the wavelength of a gamma ray. But if we talk about light wave, so light is visible light now. So let's talk about visible light. As wavelength between about 680 nanometer. Nano is 10 raised to minus 9. That means the way to look at it is that an atom is about 10 nanometers. So this is about 7,000 times the size of an atom. You make it one more zero, and it is about 80,000 times the size of an atom. And this will be 450, or let's put it 400 nanometers. So this is blue light, and that's red light. You can also say this is 700, right? If you think of it as 400 to 700 is your visible light. All the colors we can imagine is everything is in between. Each wavelength you can put a number associated with it that gives you a color that our eyes are sensitive to. So if we are talking about visible light, the smallest wavelength is 400 nanometer. Any surface which has its roughness smaller than 400 nanometers is smooth, is flat. So if roughness is less than 400 nanometer, so less than 400 nanometers, then it is flat. And metallic surfaces are classic examples of that. When we look into a mirror, we are looking on a shaded or a very thin layer of metal behind the glass surface that we have on the mirror, and they can be polished and made flat enough that you have all the corrugations in it are smaller than 400 nanometers. In that particular scenario, overall, the idea is that in that particular scenario, we don't have to talk about an electromagnetic in this manner. We can approximate. So in this particular case, this electromagnetic wave is equivalent to, can be approximated as a ray. So that's the idea of ray. This is a complicated idea to process. If you say an ocean wave is interacting with something, that is usually difficult to analyze. Instead, if you say that there is a straight line where energy and momentum is being transferred in the direction of propagation, that's very easy. A straight line is much easier to work with than you have sine and cosine waves. So the whole idea would be, from this point on, this electromagnetic wave for our purposes will be a straight line. And once you have that, if you have made that approximation, so this is an approximation which is valid if your surfaces are the corrugations in the surfaces are smaller than the wavelength of light. In that case, you can use geometry. Like geometry is the idea where you bring in interaction of lines, right? Two lines intersect to make an angle. If you have three lines intersecting, you have a triangle, and the whole geometry comes in. Once you have assumed that light goes in a straight line, which is true in this approximation, then we can use geometry to proceed ahead. And that's what we will do. All of what we will do in the next 2 or 3 weeks will involve geometry, and just the geometry of a straight line. Nothing serious. It will be very simple and mostly geometric. So we will be using geometric arguments, and the algebra will be relatively less. We have used a lot of algebra before, and now it will be relatively less. So that's our basic idea, that a ray of or an electromagnetic wave is a straight line moving in a certain direction, and the direction carries energy and momentum. How does our eyes, so how do we, since we will talk about detection of light, the best detector we have is our eyes itself. We see things around, we use light to sense it, and we would like to know, how do we sense light? How do we imagine how do we judge that that is an image form? So how does our eyes process light? We won't talk about too many details of what exactly our eye is doing. What we want to do is, as far as geometry goes, when we think in terms of geometry, in very simple terms, what content of this ray is our eye able to pick up, right? What is the content of this ray? What exactly does our eye process? So let's think of a ray of light, or let's not ray of light. Let's usually, there's a source of light. Like when we have an electric bulb up in the roof, this is a source of light. That's a source of light. And many of the sources are point sources, in the sense that light propagates from there in all directions. Once we have said that light is a ray, what we mean is that from a source, we have light rays moving in all directions equally. So that's your, the light is propagating outward from a source of light. Think of this as an electric bulb, and we will think of this as an object. We will use the word object for a source of light. Source of light will be often, the terminology here would be that source of light is an object. Trace one of this ray here, and this ray comes and goes through our eyes. So that's our eyeball, and that's your eyebrows. So this represents an eye. And now we want to see what does our eye see when you look at a source of light, what it is that it is trying to measure. So that's the ray of light, and our brain, what does it process? It doesn't, of course, see all these things, right? There is some nerve that gets activated due to this light. It doesn't see the whole line of propagation of energy. What it actually can sense, our brains are smart enough, is that it can actually sense this angle. So there is a cone of light that is coming towards you. It picks any two of them. It actually needs only two of them, but it has a whole beam of light coming towards it. It can pick any two of those rays and propagate it backward. This is our brain doing it. It doesn't see these lines. What it can do is that it can propagate it backward, and it knows that these two lines intersect at this point. But that's our abstract image. So in a sense, it can measure this angle. Our eyes, given two rays of light, can propagate it backward, and it can sense that it actually intersects there. And in that sense, it knows that there is an object there. So it's a processing. It doesn't actually know that really there is an object or not. And we will talk about situations where our eyes get fooled to think that there is an object, even though there is no object there. A classic example again is when you look yourself in the mirror. There is no one standing behind that mirror, but you see as if there is a person standing there. You see yourself there. So that's fooling your eyes, right? That's exactly what we will see. Under what situations does the eye seems to have the rays go backward, even though there is nothing in there, it thinks that it is there. So we will try to see how that is possible. When the eyes see something here, we will call it an image. So see the difference between image and an object. An object is in reality sitting there in the sense that there is actually light propagating outward. An image is when you have two rays of light coming to your eyes and it is propagated back, and you say that there is an object or there is an image there. Often, if you have an image, that means there is really an object sitting there. Image and object are identical in most of the case, but in most of what we do here, we will see that image and object is not the same. We in fact want to bring in situations where image is different from an object. That's what we will be doing most of the time here. And we will see how this gets clearly. How we will go through this will be very apparent in a few minutes, let's say. These things are called ray diagrams, since we are talking about rays and finding out how rays meet one with the other. These will be called ray diagrams. That's some of the vocabulary that we will be using. Idea is light is approximated to be a straight line propagating in a certain direction. It's not just a straight line, an oriented straight line in the sense that light is going into that object and image. We will make it clear as we proceed. Let's talk about a mirror and have these concepts clarified there. So we will have to have an empirical relation to understand what happens to a light when it meets a flat surface, and that will be called the law of reflection. Let's say we have a surface. This could be a mirror, as I said. So this is a mirror. A flat mirror in this case. And again, how do we make this? We have a glass surface and you stick a very thin metallic surface to it. If you can polish a real metallic surface, that is sufficient, but usually that is expensive, and that's why you have glass mirror. Let's think of light coming in. So for us, light now is a straight line, and that's a ray of light. We would like to know, what does a ray of light do after it meets a mirror? Like, how does it propagate from that point onwards? Does it go through the mirror? If it reflects back, in what direction does it go? Does it go back in the direction that it came in, or exactly what it does? So this is called the incident ray. This is the incident ray. To find out what happens to this ray, we draw a normal line. This is just for our reference. We have a mirror, but there is, at the point where this incident ray makes the mirror, we draw what is called a normal line. So this is normal line. And what it means is that it is a line that is making 90 degrees with the mirror. A line that is normal. By normal, we mean it is perpendicular. That's what is meant by a normal ray. Sometimes we call it a normal ray, and this is a mirror, and that is an incident ray. What happens to this incident ray? It goes in such a manner that the angle it makes with the normal line is exactly the same. So this angle theta, let's call it theta incident, is exactly the same as theta reflected. So two properties you have. One is the angle of incidence is equal to angle of reflection. And the ray that goes after reflection is called the reflected ray. And algebraically speaking, we are saying theta I is equal to theta R. That's a simple relation. This angle is exactly the same as this angle. It is almost like when you throw a ball on the surface of a wall. This is exactly what it does. It makes an angle exactly the same after reflection with respect to the normal that it was making before. The second one is that even though I said this is angle of incidence is the same as angle of reflection, it is also necessary that if you notice, I can have the incident ray coming in here, and I could have the reflected ray not really in the plane and still have the property that angle of reflection is the same. You can imagine that this is a cone, and anywhere on the cone, the angle of reflection will be the same. So we want to clarify that. So we say that all this has to happen in a plane. The incident ray, normal ray, and the reflected ray has to be in a plane. So incident ray, normal line, and reflected ray are in a plane. These two relations is what governs how light behaves when it interacts with a mirror. The idea is, the basic idea is most of the time you will have this on the plane of the paper. So you just have to think that incident angle is the same as the reflected angle. Those two angles are the same. So now with this idea that angle of incidence is the same as angle of reflection, and the idea that how eyes sense objects, let's see what happens to an object that is standing in front of a mirror. Come on. So we again have the mirror here, flat mirror, and this time we want a reference. We want to first of all have the reference that light is going in a certain direction. That's usually called the optical axis. In this case, it serves the purpose of the normal light. So let's say this is the optical axis. And by optical axis, we mean that light to begin with is going in that direction, optical. So to begin with, light is moving in that direction. That means energy and momentum is moving in that direction. So let's have this as our ray of light. That's your incident ray of light. But we just now said that if we want to see how eyes perceive what is happening, you want a cone of light. You want an object and a cone of light has to come out. So let's have a cone of light. So they basically follow two rays of light. So that's your object. And to give that object some, usually there is a height of an object, right? So there's someone standing in front of the mirror, a point is too symmetric. So let's have the optical axis as the reference and make it perpendicular to that. So that's the object. We are using only the head of the object as a reference, but once we have that, we can also talk about the whole object itself if we draw it perpendicular to the optical axis. So we would like to now know, so what has happened is that light came from somewhere and it is reflecting, right? So this is your object. This is object. Light came in and it is reflecting off. We picked two rays of light and we would like to know what happens to it afterwards. Each of these rays of light obeys laws of reflection. So whatever is this angle will be maintained. So that angle is exactly the same. So that's your reflected ray. So this is one, and that's the second ray. So this is the first ray. That's reflected. The second angle of incidence is slightly larger than the first angle of incidence. because it is made, I mean, as you can see, this is actually slightly slanted. So this angle is slightly larger with respect to the normal. So this cone widens out. So that's your cone. So that's the second ray of light. So an object is standing here, light goes and meets the mirror, and the two rays now come on this side. And let us say someone is observing here. So that is an eye here. So that's the observer. That's the eye of the observer. And now we want to ask, what does this person perceive? Like how does the brain of this person interpret these two rays of light? Remember again that this brain doesn't have the information about where these lines are following from. The only information it has is that there is two rays and it is possible for it to project it backward. So when it comes to this person or the brain of this person, it is going to project these two rays backward, and it doesn't know that there is a mirror here. It will go all the way backward here. And I'm using dotted line to represent lines that actually light is not taking. It is just a perception of this brain. So it projects it backward, and it seems like it is meeting here. And according to this eye, wherever these two rays of light meet in the backward direction, there is an object there. And from the perception of this eye, this is an image. So this is an image. There is nothing in there actually, but it seems to this person that all this light, which is actually coming from here, is originating from this point. And that's what this person perceives as an image. So you see an image in there, and you draw this here. So that's your image. Object is standing there. In fact, you can shield this region completely so that light cannot go through here. So it seems magical that you will actually go and try to touch that person. That person doesn't exist. It's equivalent to saying that there is a mirror and you're seeing someone in the mirror, but you don't see it in the horizontal direction. If there was a wall next to you, then you don't see the person itself, but through the mirror you can actually see the person. We are experienced enough, or we have gained the skill that we can interpret this even though there is a wall. The moment you see something in the mirror, we know that, oh, this is how our brain perceives. So we have countermeasures to this, but in general, as a surprise, if you're not used to the environment, it is possible to fool yourself using these tricks. And earlier, of course, these were used as magic tricks. It is good to analyze at this point, how far is this image? So if you're so much distance in the front of the mirror, where exactly is this image formed? How far is this image inside your bathroom mirror, let's say, for that purpose? And most often, once we have convinced ourselves that this is how the perception of our eyes work, often it is sufficient to work with one ray. Whenever you want to ask, how does your eyes perceive, then you want a cone of light. But for most of the measurement purposes or algebraic purposes, when you want to know how far is the image, how large is the image, in those cases, it is sufficient to just have one ray. So there is no need to have the baggage of two rays with us. We will carry only one ray. So how does the one ray diagram work? So again, this is your optical axis. That's your mirror. That's perpendicular to the optical axis. That's your mirror. And we have light coming in from here. That's your object. Notice that the object is always kept perpendicular to the optical axis. Let's say the height of the object is h initial, or HO, right? Height of the object. Height of the object. How far is it from the mirror will be your object distance. And let's call that P. And we would like to know, after reflection, it has come in this direction. So that's your angle theta. That's angle theta. But we will project this backward. And we have argued that it is at a certain distance that you have your image. But how do we find that image? We need two rays, as I said before, but we don't have to really take this cone as our reference line. We can draw a very big cone. So that's your second ray of light. The second ray of light has been chosen in such a way that this makes an angle zero angle of incidence with respect to the mirror, so that after reflection, it goes back. That's your reflected ray. So this is your first beam, and the second beam this time has been chosen not as a tiny cone which can actually enter the eyes. These two can enter the eyes if you think of our eyes as really huge. Like that's your eye, and that's the eye, and those are the two rays. You make it move backward, and wherever it beams, that's your image. But these two rays are much easier to analyze because they form a triangle, and that's your image. This we will call height of the image. And how far is this? That we will call as Q. That distance will be Q. So some nomenclature here. P is object distance. And in this particular example, this come out to be simple and straightforward, but we are going to talk about curved mirrors, in which case you will look funny inside the mirror, and in those cases this is not obvious. P is object distance, Q is image distance. Height HO is height of object. And HI is height of image. And now we can ask, what is the connection between height of the object and height of the image? If this is angle theta, we don't even need to know this angle. There is some angle theta. That's the same as this angle theta here. So if this is angle theta, that's also angle theta. Right? That's the same line projected backward. So that's angle theta. So we have two triangles with the same angle theta here. And we just have to ask, what is the connection between height O and HI, and it comes out exactly height of the image is exactly equal to the height of the object, because we are having this base exactly the same, and if you were to project it backward, just geometry tells you that height of the object is exactly equal to the height of the image. In this case, it is slightly straightforward, but we will do more non-trivial scenarios where, especially when these are curved mirrors, and we will see how we have to analyze this. But before we go into that, I want to give one simple example where it is not really one mirror. Now that we have one mirror, we can actually extend this to two mirrors, three mirrors, and they need not be parallel. They can be making an angle, and sometimes you see this in a museum where you have two mirrors kept at an angle. In fact, you can try this in your bathroom also. If you have two mirrors on a corner of the room, and if they are not at exactly 90 degrees, most of the walls meet at 90 degrees. If they're not at 90 degrees, then you can ask how many images of yourself will you see? So let's do that simple analysis here. So let's have a scenario. So these are compound mirrors, flat. This also is one of your homework problems. I'll do this for 90 degrees and then we can generalize this. So we have, let's say, two mirrors making 90 degrees. And let's say this, the object itself is just kept asymmetrically. Notice that this is closer to one of the mirrors relative to the second mirror, right? So it's not exactly the same, equidistant from the two mirrors. This will clearly make an image here, so that we have said that our image is formed exactly the same distance into the mirror. So that's down here. So that's your first image. It will also make a mirror image here, and that will be somewhere. So it is clear that there will be two images formed. But if you were to actually check it out at home, if you were to have two mirrors in this manner, it will turn out that you will see three images. So, and then the question is, how is the third image formed? So let's have a ray diagram doing this. So let's say one of the possibility is that light can go this way, and you make a small cone here. That's your ray of light, and you can have two rays projecting outward. And if you stand here, you see this as your image, right? So this is your object. And let's call this image 1. So there is someone standing here, you move your head around, and in this particular direction, you see an image of this object. You do the same thing in here. And this can reflect back in this direction, and again make it two rays, and you see that it can be projected backward, and that's your second image 2. But where is the third one? You can actually see that you can also go from here, go reflect back this way. So this is double reflection now. Notice all these were single reflections. Now double reflections leads to a ray of light going this way. Again, make a cone out of it, which keeps growing in angle. That's your ray of light. And if you were to draw this correctly, this will come out and meet exactly here. And that's your, let's say that's your image 3, which is exactly making a rectangle here. In fact, it can make multiple reflections like this, but they will all overlap over each other. And in your homework, you do this for two mirrors making an angle. Right? One of the problems says if it is 60 degrees, then how many angles will you form, and so on. I'll stop here. And we'll come back and talk about spherical mirrors, in which case the mirror is not flat, it's actually circular in shape, and what kind of mirror or what kind of images are formed in here. Is it straight, or is it smaller or bigger? Thank you.